Before I start explaining you how to calculate the amperage and the voltage on an inductive circuit plus capacitance circuit, I need to explain you some extra concept. First of all, if we consider voltage, and as I told you, the voltage could be in a motion describing different opening in regards with the reference, which is 0. When it's opening, and we have this opening, theta is there, and is theta equal to 20 degrees. So, and we consider the projection of theta on the horizontal, on the vertical axis y, and the projection on the horizontal x. This is known as the sine function, and this is known as the cosine function. And so the tangent function is equal to the sine function divided by the cosine function. Okay, that is the first concept. And keep in mind, this is a trigonometric function, and because we are talking about the voltage represented as a piece of line that has a value and it describing some angles, some opening in regards with the reference. Why this opening is produced? When you install inductance or when you install a capacitance, there is a different opening with the voltage that you are, when you apply the voltage into a inductance or when you apply the voltage into a capacitance. So if we have the voltage applied to an inductance, okay, represented by L, so we can represent the source voltage VA as when VA is here. So the voltage that will be induced and produced by the inductance will be 90 degrees ahead, okay, in regards to the VA, the source voltage. Okay, so if we have a capacitance, in a capacitance, and we have VA, 120 volts. So right here on the capacitance, when we have a capacitor, so we represent always a zero degrees the VA voltage, the voltage by the source, and the voltage on the capacitance is 90 degrees behind. Okay, so the voltage on the inductance is ahead, 90 degrees, and the voltage on the capacitance is 90 degrees behind in regards to the voltage on the source. So we have three concepts to keep in mind. First of all, when you have the vector is a piece of line that has a value, also that is, it could be positive and negative, and additionally, it could be describing an opening in regards with the horizontal line. So right here, what we have here is that the line that is opening, the vector, the voltage, is describing some opening in regard with the source voltage, and this opening is the theta angle. And when we have some opening, the projection on the vertical x is, or y, is known as a sine function, and the projection on the horizontal is the cosine. If we divide the sine function by the cosine, we have the tangent function. That is what we need to understand. And normally on a circuit in which you have just a resistor, it's easy to apply the Ohm's law, because the Ohm's law is telling you that the voltage VA is equal to the resistor times resistor 1, times the amperage produced by this external force. And we can divide the voltage by the resistor to have and calculate the amperage. But when we have a capacitance and inductance, it change a little bit. So we need to define that the resistance represented to the source by the inductance is calculated and represented by XC is equal to 2 times phi times the frequency times the inductance. This is 2 times 3.1416 times the frequency 60 Hertz times the inductance in henries. Okay, for example, if we have XL, because it's an inductance. So if we have an inductance whose value is 6 henries, so we are going to have the resistance, the inductance resistance presented by this coil will be equal to 2 times 3.1416, which is the constant phi, times 60 times 6. That will be the total value, and this will be equal to 3.14 times 2 times 60 times 6, 3,768 ohms. That is the way that we calculate the resistance represented or presented by an inductance to the external force of voltage. Okay, and that is that we calculate this. So if we have that is the inductance. In a capacitance, if it is the opposition, the ohms presented to the source voltage by a capacitance is calculated by Xc equal X sub index C equal to 1 divided by 2 times the constant phi times the frequency times the capacitance. For example, if we have a capacitor that is 5 microfarad, for example, very popular on single phase electrical motor, 2 times phi, 60 Hertz times a microfarad is this. Okay, and we do that math, and we are going to have 2 times 3.14 times 60, 2 times 3.1416 times 60, times 0.00005. This is equal 1 divided by 0.0001 18. Okay. And 1 divided by 0.00018 this is equal to 5,307.8 ohms. Okay. This is the way that we calculate the ohms per inductance and the ohms per capacitance. When we calculate the inductance, so the inductance in parallel, you calculate the inductance in parallel like a resistor. So here the total, of course, first of all you have to calculate the independence ohms on each of them, and then when you have that, you will be calculating the total inductance that will be equal to 1 divided by 1 L1 plus 1 divided by L2. And here, keep in mind, these are ohms. For example, if I have two inductance and each of them is 3,768 ohms. So if this is 3,768 ohms, and this one is at 3,768 ohms. So you can calculate the total inductance in ohms applying this formula. That will be 1 divided by 1 to 3,768 plus 1 divided by 3,768. Okay. Now keep in mind, first of all, you have to calculate using the Henry's the impedance in ohms, XL, that is equal to 2 times the constant phi times the frequency times the inductance in Henry's. When you have both values, you apply this formula to calculate the total ohms. In my example, it will be, let's do this math. One divided by 1 divided by 3,768 equals 0.00026 plus 0.00026. This will be 1 divided by 0.53 in ohms. Keep in mind, we are going to calculate because these are ohms. 1 divided by 0.00053 is 1,886.7 ohms. This is the total resistance. One more time. The inductance, when you have inductance in parallel, what you will be able to read as a specification for the inductance is the Henry's. If you want to connect the inductance in parallel, you apply this formula. But before you do this, you need to calculate the ohms that each inductance present to the source of voltage and apply this formula. In my case was The ohms for each of these is 3,768 ohms and 3,768 ohms. Both of them in parallel. Apply the formula, and these two inductance represent or present to the source of voltage a total resistance of 1,886.7 ohms. Okay. Because the inductance behaving like a resistor, when you have them in a serial circuit, and this is 3,768 ohms, 3,768 ohms, the total here, total resistance presented by these two inductance is equal to R, both of them, because they are behaving as a resistance in a series circuit. 3,768 times 2 this is equivalent to 7,536 ohms. Okay. That is the total resistance when you have in series, a series circuit. Now, we are going to calculate the resistance presented by capacitor. The capacitors is the opposite, behaving the opposite way than resistor. So we have capacitor. Capacitor 1, capacitor 2, and this is 5 microfarad, and this is 5 microfarad, and I connect this in parallel. So the total resistance presented by the capacitor, both of them, will be this, because they behave on a positive way than the resistor. You just add. So the total capacitance will be, so on this way. But before I do this, I need to find out the ohms that each capacitor represents to the source of voltage. How do I calculate this? This is XC1, XC2. The resistance by a capacitor is calculated, divided 1 by 2 times the constant phi, times the frequency, times the capacitance in microfarad. So this will be 1 divided by 2 times 3.1416 times 60 hertz times 5 microfarad, 0, 0. Okay, and this will be, let's do the math, 3.14 times 2 times 60 times 0.000005. This is 1 divided by 0.001884. And these are ohms, so 1 divided by 0.001884 is equal to 520 ohms. 530 ohms. Let me double check. 0.0 2 zeros, 3 zeros, 4 zeros, 5 zeros, 5 times 60 times 3.1416 times 2. Yes, 0.001884. Okay, 1 divided by 0.001884 is equal to 530 ohms. Okay, so each of these present a 530 ohms. So the total resistance presented by these two capacitors in parallel is equal to 530 ohms from the first one plus 530 ohms from the second one, which is equal to 1060 ohms. So when I have, this is the way that I calculate the ohms on capacitors using this formula. Then if I connect them in parallel, the total resistance is calculated on the opposite when you have resistor in parallel. You add just the ohms on each capacitor. If you have the same capacitor in a serial circuit, they behave. So let's say that we have capacitor 1 plus capacitor 2 in a serial circuit. So we apply this formula. The total resistance presented by both capacitors, we apply the formula. When they are in a serial, they behave as resistor in parallel. 1 divided by 1 by XC1 plus 1 divided by XC2. So this is the capacitance is given in microfarad, 5 microfarad. This is 5 microfarad. I need to calculate the ohms by using this formula. Xc is equal to 1 divided by 2 times the constant phi by the frequency times the capacitance in microfarad. In our case is 530 ohms, so I calculate the resistance presented by these two capacitors in serial, and it will be 1 divided by 130 ohms plus 1 divided by 530 ohms. And this is equal to 1 divided by 530 ohms times 2. This is equal to 1 divided by 0.00373. 1 divided by 0.003773 is 265 ohms. Xc in this case here is equal to 265 ohms. 265 ohms. And this is the way that you calculate the total the total resistance presented by inductance and capacitance. Okay, when you do this, this is known as impedance. Capacitance impedance. If there is an inductance, is inductance impedance. Impedance represented by letter C. So this is the total impedance presented by a capacitor in a serial way, and this is the total impedance presented by two capacitors in parallel to the source. So we are talking about inductance impedance and capacitance impedance before we move on and apply Ohm's law.